Welcome back, and today we're going to study the natural log or logarithmic functions and their derivatives. We're really going to focus on the natural log, though. Okay, so it's more singular than plural. Um, Maybe we'll expand it to log of any base number, but the natural log being the most important one to study. Um, Here we go. We're given a function. Here's the problem we're going to start with. We're going to start with here. We've got this. We want to find the derivative of this natural log. Now you know what this function looks like, right? I'll just draw it over here. This is another one of the functions you should know. You should know that it goes to infinity as x goes to infinity. And as x gets closer to 0 from the right side, it goes to negative infinity. The domain just goes from when x is greater than 0. Okay, so this might be called the natural log. Okay, in order to find the derivative of this, I could give it to you, but I think the derivation maybe is a little bit instructive in this case. Okay, this function is called inverse. This chapter is about inverse functions. I don't know, I'm going to assume I do not know the derivative of this function, the natural log, but I do know what the derivative of its inverse is, right? I know if y is equal to e to the x, dy dx is equal to e to the x. I know that one. I know e to the x is the inverse of the natural log. So I'm going to use that property in order to find this derivative. Well, how do I do that? Okay, I start here and I take the inverse of both sides. I take e to the x, okay, e to the y, sorry, and e to the x. So I apply the same function to both sides of the equation. And now, what do I get? I'm left with e to the y is equal to x. And now I want to find dy dx, right? Well, this just looks like a what? An implicit differentiation problem. So we can do this. We know what the derivative of e to the y is, so let's get on it. The derivative of the inside here is just dy dx times the derivative of the outside is just e evaluated at the inside. What's the derivative of x with respect to x? Well, that's just 1. Okay, so what did I just do? I just took the derivative of both sides with respect to x, right? And I get down to this. Do a little work on this, and I say, well, dy dx is equal to 1 over e to the y. Now, so here, what does this give me? This is true, but this gives me dy dx as a function of y. I'd really want dy dx as a function of x. So, well, what is y equal to? Well, y, remember, y is just equal to the natural log of x. So why don't we just plug that into here? So that's equal now 1 over e to the natural log of x. Okay, well, what's this? These are inverses of each other. That's just equal to x. So what did I just find out? I found out dy dx is equal to 1 over x. All right. So what's my result? The derivative of the natural log of x with respect to x, this is flashcard material, is equal to 1 over x. That is an important derivative you need to know. And with that in mind, I think we can do this on the same page. Let's go up here. Remember, what would this be then? The integral of, well, let's do this, 1 over x squared. See, the derivative of 1 over x, the integral of 1 over x squared is just going to be the integral of x to the minus 2 dx. Right, and then we applied our power rule. This was just x. We powered it up to minus 1 divided by minus 1 plus c. So if I would have, by mistake, given you this integral though, you would have said, hey, that's equal to this. Now, if you try to apply the power rule on this, you'd get e to the 0 over 0 plus c. And this should immediately alert you. If you try to do that, that is a problem. That is wrong. Okay? What if we just found out? What's this? What is the integral of 1 over x dx? That's just going to be equal to the natural log of x plus c. Okay? So, one for the flashcard, 2 for the flashcard. Do we need to prove this? What's the derivative of the natural log? Well, the derivative of the natural log, the derivative of this side is just going to give you that back here. So we've got an integral and a derivative pair for the natural log. The natural log is what? Just another function here. Another function. We know how to take its derivative. We know how to take the integral of its derivative. We did a little derivation of, we found the derivative from the derivative of its inverse e to the x. Now what do you think we want to do? Oh, how about we review some other parts of calculus by working problems with the when we need the natural log. So let's, I'll set up a couple problems on the next page. We'll get started. Okay, here I'm given a problem that's a natural log of a function. We got a composite function, a function of a function. Here, let's go to blue maybe. And we want to find, remember, finding the tangent line at a particular point. What do we need to find a tangent line? Well, we need to find the derivative. We need to find dy dx at what? At x equal to 1. And we need to know the point which they gave us. Is this, they could have just given us what? At x equal to 1. Then I had to plug this in. And, oh, this doesn't. The natural log, okay, so what is this saying? If I plug this in, this is saying the natural log of e is equal to 1. So it is indeed true, but you could have plugged x in there and figured out that y is equal to 1. It wouldn't have had to give you x and y. But anyway, as you can see here, we need to find the derivative. Now there's an easy way and a hard way to do this. If you notice properties of logs, and let's just talk about that. We'll go to the easy way first. You got properties of logs, right? This is the log, the log of a times b is going to equal to the log of a plus the log of b, natural log of b. That's going to be true up here too. Y is going to be equal to the natural log of x plus the natural log of e to the x squared. Well, here we got another property of logs. What is the log of a to the b power? Well, remember, you could bring that b out front. That's equal to b times the natural log of a. So this is an exercise in knowing derivatives and properties of logs. This is going to become x squared will come out front, correct? Because that's in the exponent. Then it's going to be the natural log of e. Well, what's the natural log of e? These are inverses of each other, right? The natural log of the exponent, that's like saying the natural log of x to the first power, right? So the natural log of e is equal to 1. So this whole thing, with a little bit of properties of logs and remembering what the inverse was, here's the function. Another way of writing the function. Now the derivative is quite a bit easier. And I've seen this kind of work show up on a real problem on an AP test, where they're really testing it. It's a very simple problem once you apply properties of logs. Now what is dy dx? Well, dy dx is merely equal to 1 over x plus 2x. There we go. Well, what's that equal to at x equal to 1? That's going to be equal to 1 plus 2 equal to 3. Okay, now I need my tangent line. Let's go back to, what are we going to do? Let's do the tangent line in green. Tangent line in green, right? So I'm going to say 3 3 is equal to y minus 1 over x minus 1. I write it like that, and, and then I change it. But this says this is the slope of the line, right? The slope of the line is 3, and this tells me if I calculate a slope on any point yx on the line, better be equal to that. And then, of course, here's a more common form. If you said y minus 1, I multiply both sides by x minus 1 is equal to 3 x minus 1. You could stop right there. Tangent line. Stop right there. You don't need to multiply these out. You don't need to give this as y equal mx plus b. This is perfectly acceptable. Okay, let's continue. Let's get another problem here. Now remember this problem, properties of logs, knowing the derivative, the natural log, and a review of what does it mean to find a tangent line. Okay, how about this? Oh, okay. Solids of rotation. The solid is defined by what? These. So I've got to draw a picture. First thing I've got to do, let's draw a picture. Maybe I could do this over here. Again, this is, what is the function 1 over x plus 1 equal to? Well, at x equal to 0, that's equal to 1. 0, 1. And then as x gets bigger, this goes down. 1 over the square root of x plus 1. Okay, and it's going to go, oops. Seems like I need to define y equals 0, 2. Okay, it's really this. They want this. Probably should have said y equal to 0 also. Because they want to rotate that about the x-axis, right? So we're going to take this thing, rotate it that way. Well, this is what, it's going to be easier to cut, to make my cuts perpendicular to the axis of rotation. And I'm going to get what kind of cross-section? I'll get a cross-sectional area. It's a washers or a disc problem. I've got my area. I'm going to integrate a of x dx. The area of my disk, I'm going to integrate from 0 to 1. Well, what's this? What's that radius? That radius is merely this height, which is 1 over the square root of x plus 1. So then a of x is going to be pi r squared, or pi over 1 over x. Okay, and you're going to find out where we got an integration problem. 1 over x plus 1 from 0 to 1. Well, can we integrate that? It's an integration problem. You might guess we need a natural log because it's in this section, and you'd be correct. In this case, you could do substitution. Substitution, but you could also, how about if I work substitution? I'm just going to give you an answer here. X plus 1. It's the natural log of x plus 1. Pi from 1 to 0. Is this, and then is this the antiderivative of that? Well, what's the derivative of the natural log of x plus 1? It's the derivative of the inside, which is 1, over the derivative of the outside. The derivative of the outside is just 1 over x plus 1. So yes, the derivative of the natural log of x plus 1 dx is indeed equal to 1 over x plus 1. But feel free to use substitution and turn this thing into 1 over u. Okay, let's finish evaluating this. This is going to be pi times the natural log of 2 minus the natural log of 1. Right? Now, what's this? What is the natural log of 1 equal to? That's something you need to know. The natural log of 1, that's equal to 0. That is 0. Okay, so this whole thing, the answer is going to be pi times the natural log of 2. Okay? I could work a shells problem here too, but maybe, actually, let me do another derivative with a natural log real quickly. Let's do and since we're almost at 15 minutes, we don't want to go over that. I'm going to say, how about y is equal to the natural log of x to the 5th plus 3x. Oop, getting sloppy in my speed here. That's a 3, believe it or not. Okay, and I'm going to find dy dx. Well, that's going to be equal to, what's the derivative of the inside? That's 5x to the 4th plus 3. Okay. Times the derivative of the outside. What's the derivative of the natural log? It's just 1 over something, right? 1 over x, 1 over the inside, or x to the 5th plus 3x. Okay, so another little chain rule, taking a composite function with the natural log as one of the functions. Okay, so that's a review. We added a new function. We added the natural log. The derivative of that is 1 over x. We reviewed a chain rule, a tangent line problem, and a volume problem. Next, we're going to look at some inverse trig functions. See you soon.